Okay, so let's get started slowly. Hope people are coming back. All right. 河道那边的同学们尽量尽快的这个到位啊！我要求河道那边老师最好是这个 take 一下课程结束以后，还是 take 一下 attendance 啊，我们得了解一下学生们不能这个，尤其是河道那边啊，很多学生不能让他们就是远程的去随随便便看一下 video 啊。那以后我也就把 video record 下来，直接放就好了，对吧？大家看过那个美国那个笑话，对吧？电视剧那个，很多学生们到课堂，那是原来还没有这么像这个有互联网的时候，原来那个地方学生，但是那个时候有录音机的时候啊，很多学生到课堂上就放一个录音机在自己座位上啊，就离开了，跟老师讲完录下来，他自己回家听。后来第二天老师上课，我就带了一个播放机放在那儿，然后就走到了，录下来就走。All right. Okay. Let's get back to. We have some time about our. I'll see how far we can go. Now, see with the preparation. Now, if we start to get into the rest of the course, we're going to be. See, as I said, there are not many good new ideas, right? So the rest of the lecture, we're going to get into heads on the heart of the course now, and also we're going to be very, very fast. Okay. The fact is both slow and fast. You see, right? You can see it's actually a lot of things. Once you have really understand the history, the concepts, right? The basic concept ideas from the history, the analytic approach. Now, the rest is actually how to apply those ideas and concepts now to a more general setting. That's it, right? And so. This is how we learn more general distribution rather than this linear wise. So, right? But first of all, I mean, again, that's why you need to be there. Of course, I think the homework 2 was released. We'll do October 9. Make sure you do that by October 9th and deadline. And this is for both, right? This is for both. Why do I have this schedule? This is for both Hotao and Hong Kong U, I believe, student. And also, as I said, for Hong Kong U students, we will have a final project. Okay, this is a series, right? As I said, there's no exam. I mean, graduate school, graduate students, I don't test you, right? It's up to you how much you grasp. Your job to learn to use, right? You learn to use. There's no point for me to test how good you grasp knowledge. Right? If you don't know how to use it, it's useless. So try to use what you learn in classes or related to the topic in the final project. So you are allowed to. The format is following. Around the end of the month, October, we will give a midterm presentation. You have about 1 month. You're allowed to make a team of 2 to 3 people. If you don't have a team yet. Time to start, okay, as early as possible, right? Don't procrastinate, okay? 2 to 3 people, and better find people with complementary background, complementary skills. Right. I did my first course project at Berkeley. We did a computer graphics course, re-rendering. I worked with a student from physics department, one from CS division. I mean, it's EE, right? Right. So the 3 of us, we learned a lot from each other. Try to make a team that people are, and also end of the October we will make the presentation. We want 3-page, white paper, basically formulate the problem. What you probably choose, and we will probably in the between try to release some tools, AI tools, see if we can help you too. See, there's all kinds of tools. There's there are AI deep research tools. We'll see if we can release quickly with Huang Cao Lao of STA. We'll probably see if some of the tools can help you to formulate your problem at least do some survey better, okay? Research, just think about the course project as a mini research project, okay? And you have to practice, right? This is your best time to do something reasonable research. If you cannot even do a good course project, forget about research, okay? Better research project, right? But research, well, this is research. It's a research is why it's called research. Search, research. Right? You start with search, right? Survey papers. Okay, do that, and do a good survey, right? And you give a presentation. It's team. Well, depend on how many team. Maybe 5 minutes to a few minutes. Just pitch. Tell me why what you want to work on. Why? You know, why it's worth your time. Okay, even bother you to do. Or if you are successful, what is value? Anyone can learn to others. Okay, you have to justify the problem. Don't tell me results, right? So the students always approach the problem with a given prediction, always very rushed. Oh, I want to show you I can do better. No, don't do that, right? Oh, this is what I did, right? This is someone didn't try this. Tell me the method, solution. Right? Between the problem, justification for the problem, and the solution to the problem, and the results. Results are least important. Solution is the second. The most important is actually the problem. Why in the world do you want to work on that? Okay? Oh, because people haven't thought they did this, I grabbed this paper. Oh, they tried this, they haven't tried, they didn't thought about doing this, right? Had a slightly better idea, I make it another 1% improved, right? Don't do. Oh, they didn't use this new data, right? Think about it. Why do you bother with the problem? Why is the problem worth your time? The problem is important. Justification for the problem. Find the good. I can always tell you, right? Asking the right question is far more important than how to solve it. That's why that differentiates great mathematicians from mediocre ones, great researchers from mediocre ones. Okay. A lot of great mathematicians or great researchers are remembered by the question they ask, not the solution they provide. Okay. 所以这个讲讲 ，OK， this is a chance. So you have nothing to lose, right? Be a little risky. Think out of the box. It's not your professor giving you some project you have to do, right? This is your course. It's your time to. So what you fail? What do you feel? You want to learn a lesson from it. Even towards the end, even you did not know results, as long as you justify your problem, if your approach turns out to be not working, at least tell me what the lesson you learned. Very valuable lesson. And everybody else in the class can share. You find it valuable. That's great. 明白吗? I know this is not natural for most of you, especially in Chinese students. You guys are not natural. Trust me, I know, right? Most of you just try to grab some papers. Right? Your professor asks you to read or something. Oh, I want to improve on it. No, don't do that. This is not an opportunity to do that. Right? Do something, interesting together. Change each other a little bit as a team. All right. You guys propose ideas, have a discussion. Why in the world I want to waste my time with working on your problem? Right? If you're not exciting, if it's not meaningful, it's not significant, why should you do that? Right? So this is I hope you to. Right? I hope by October, end of the month, start now. Start today, tonight. Right? Exchange emails, messages, WeChat, build a group, right? Talk to each other, kick people out, bring people in, okay? Marry each other a little bit, right? Do your marriage, right? See, do shuffle about team. Right? Propose some ideas early. During the next couple of weeks, 1 week, to think about it. Do some profuse reading. Right? Related topics, papers, right? Share, and then formulate. You add a couple pages. So the final project will be the final weeks. This after the during the final exam, we'll find the proper time works for most of people. So you'll give a final presentation, maybe 10 minutes each team, and you'll write a paper report. The report will be exactly like in your format, whatever. We'll probably just decide here whichever one I care, whoever, whichever format template you use that, as if you are writing a your paper. Okay. I hope some of you probably even be able to publish. Right, that's the idea. Write a meaningful paper. Right. Together, worse publication. Again, publication is not the goal. Okay, but it's just the process. And you can use whatever tools, even AI. Okay. See, we're going to probably even provide some tools for you to help you. But do better. Show if you can do better. With the support of AI assistant during this process, find out if any of if AI tools can already replace you, right? You can already replace you, you'll be in trouble. Okay, your job will be very in trouble in the future. Right? So you find out how good they are, how good you are against the AI models. Okay, anything you can do better than AI models. You are encouraged to do that. And also for the slave people, right? The 河套的这边同学 you are welcome to join. I encourage you to join, right? You guys can do some, maybe the TA can help. I can ask him to help a little bit, or some of the TA can help, maybe say and can do some matchmaking. Some of the students from Hatao, you are not required to do a project, but you are welcome to join, okay? Whoever in the Hong Kong side, there's some team, maybe especially by midterm, you can start early. You can do some exchange. We can do some mechanism of exchange, but at least by the end of October, you are welcome to join the presentation. You can do the Zoom. If you find some project you're interested, you are welcome to join the team, right, to contribute. Right. Okay? All right. So let's recap a little bit. So what we have done so far, right? We talked a little bit about the history of intelligence, right? In general, the overview. That's chapter 1. And in chapter 2, we also did an analytical approach to linear models and also mixture models, right? PCA, ICA, dictionary learning, complete cases, over complete cases, right? ISTA, so on, right? You should be very familiar with that. Now, that is the best today. People know about linear models, analytic approach, right? You can write down the distribution with clear mathematical distribution. And also we can very much write down either closed form solution or at least very efficient optimization algorithms with the theoretical and complexity guarantees. Okay? So this is you can say this is the body of knowledge. Very complete, very clean. Right? We know almost everything. And also we talk about, right, in order for we use the ISTA, right, over complete cases. In some cases we don't have we have to resort learning the dictionary using optimization. We saw the connection between deep networks through the eyes or perspective of on-road optimization, 对不对？通过把优化展开得到 deep networks. Okay. Now, of course, this is analytic models, right? Mixture Gaussian, some places those are nice, but what about the distribution of images or natural languages? I don't even know how. It's a linear model? Of course not, right? It's some surface, I don't know. How many dimensions? I don't know, right? Mixture Gaussian? Probably. Who knows, right? Mixture Gaussian of different dimension? Probably, right? You don't know. How many components? I don't know, right? And again, so how do we do? But of course, we started this lecture beginning. I see those distribution has structure, right? If they don't have structure, it's not worth learning. They have those low-dimensional structures, right? They carry information. Carry information allow us to predict, to generate, right? Hence, we know they're low-dimensional, but how do we get hold of them? How? Right. So we know how to do this. or the analytic ones, all the classical methods, all about the analytic ones, right? If we know the dictionary, we can use the dictionary to do denoising, to do filtering, to do projection, to do extrapolation, right? That's least square, linear filter, Kalman filter, sparse codings all doing that, lasso all doing that，对吧？这大概100年的历史啊，100-200年的历史，100 years history people working on linear models or mixture of linear models. If you don't know the dictionary, if you don't know the base, you learn it. Power iteration, PCA, right? Dictionary, fixed point algorithm, iterations, system ID. If it's a dynamical system, you do system ID again. If it's linear system, it's essentially PCA, right? And if not, if the mixture Gaussian, then this time. Overcomplete this time, right? You can do that. Well, general data distribution. It's a little bit harder, but conceptually shouldn't be that different, okay? 所以概念应该是一样的，对不对？都是定位结构嘛 ，should be the same. But maybe it requires slightly more general solution. More unifying view. How do we approach low-dimensional structure? Right? We have to find an approach that is unified all the classical. Those classical analytical model must be a special case. Okay? If you find a unifying perspective, there must be, so whatever general solution you find, it also sure works for the PCA, works for the linear subspace of picture. You know what I mean? Right? So how do we approach this? Again, as I said it before, right? How do we measure the volume, the dimension? Entropy. Right? Entropy is the generalization of volume. Let's need to get used to it. Right. So if you have X sample, it has probability P. What is the number of? So basically, entropy looks a little bit weird, right? Minus log PP. What the heck is that? Turns out it's very intuitive. 对吧？所以真正的看似很深奥，它都在数数啊，数的很简单啊。So if an event X has probability P, let's say P is a half, 0.5, okay? In B, head or tail. Now how many bits you need to represent in that event? 对吧？01这个 base 是应该是2啊，我们用2就是那个对吧 binary 啊。当然有时候有个这个 base 无所谓，就是差个常数而已，对不对？啊 ，if 0.5 log 0.5 is 1, right? Minus, sorry, log 0.5 is -1, and minus 1 is 1, OK? 1 bit 01嘛。如果是 1/8 1/8是多少？3个 bits 嘛。从0000、000到001、002、011，对吧？数嘛，3个 bits，对不对 ？binary bits. One of them, you have to tell me which one. So you need 3 bits to representing an event X has probability of 1/8，那么简单，是不是？所以 log 1/8 is exactly -3, minus the 3 bits. So this is precisely counting for every sample X. How many bits you need? Then do expectations. Some variable takes 2 bits, some shows 0.5, some shows to 0.1/3, some shows up. Everything should sum up to 1, 对不对 ？X is a random variable 嘛 ，and all possible value, the probability sum ups to 1, 对吧？1/8、1/4加上另外一个1/4，再加上一个1/2就够了，差不多，对不对？好，还有一个1/8，anyway，你自己去加起来，对吧？加到所以就把所有的 events 加起来 ，every event how many bits to code them? Low expectation average. Because every X shows up with what? Sorry, I should have wrote this down. It should be 5 H's. So the expectation is, this is actually equal to what? Integral P of X multiply this one, dx, 对不对 So this one is minus p of x log px, right? P is what? Px. Why do you multiply px? Because px is how many frequency the probability x shows up, right? Once x show up, that's how many bits you have to pay to store it. But it shows up with the probability p, so let's take the average. 明白吗？所以这就是 how many an average when x as a variable when with certain probability px shows up. This is how many bits you can store such event， 对吧 ？Clear？ 想得通吧？赶紧把这不懂的提出来啊！这个很简单的啊。这就是 once px shows up，once x shows up， this is how many part， 就是有多大个袋子去装它，对不对？多少个 bits 装它嘛，描述它。Of course, every x with the p of x show up， 所以 take expectation， 取个平均啊。所以这就是 entropy。So entropy just how many bits to store x on average. It's a random variable. It's a volume. 只是你用多少个字节离散的空间来装它，对不对？都知道 volume dimensions 都在 measure 体积吧？对。You can think about it. This is a generalized notion of dimension, generalized notion of volume. Okay, different metric. This is actually 非常this is Sharon 的 stroke of genius. OK, Sharon 的定义啊，非常了不起。当时大家原来就不太清楚怎么去 measure information 啊，这就是 how we measure the volume of the data 啊 using entropy defined this way. Now you can talk about the information in a quantitative way. You can measure it now， 对吧？所以为什么大家看发现？所以你现在明白对不对？为什么你看为什么大家物理一旦明白这个东西，就会发现很有趣的一件事情，对吧？物理学家这样讲，黑洞不被 destroy information。原来听起来很玄，什么 what the heck is information，right？因为你看，Wiener Norbert Wiener 也讲过，对不对？这个宇宙世界上啊，对吧 ？Information is the third independent quantity notion, independent from 那个 energy and volume of energy and mass. OK, energy and mass. 实际上我们也知道 energy 和 mass 是可以交换的，对不对 ？energy 和质能方程嘛 ，energy 和质能。还有宇宙另外一个量，空间的时间，是不是？物理里面就两个量，一个是 energy 质量和 energy， 对不对？这两个是互换的。还有两个量，时间和空间，这两个量也是可以互换，对不对？关于那个相对论里面，时间和空间是可以互换的 ，OK？ 对吧？空间为什么 information 不会消失是什么意思？空间不会消失，只会被压缩啊，只会扭曲，但它不会消失。实际上 information 黑洞不能消失，它实际上是空间被扭曲了，时空被压缩了啊，被扭曲了，它实际上并不会把它压到没有啊，只是变了。而且时间是怎么定义的 ？Ultimately 的宇宙时间怎么定义？时间简史看过吧？你看过，咱看这个我们还学 science 的时候。霍金讲的时间怎么定义的 ？The change of the entropy give the direction of time。所有时间定义都是 change system change， 这是 change 怎么定义？都是跟 entropy 有关啊，空间的变化啊，扭曲变化有关。OK。所以你看 time and space actually related。Energy and mass is related。就这是 two different 东西，所有东西实际上都是空间的变化。质量在空间的 concentration 决定能量的质量 ，OK， 导致空间的扭曲，所以到最后全部可能宇宙就是空间的密度扭曲在变化，时间也是空间的变化。So this is actually string theory is actually doing this, right? String theory actually try to unify everything as twisted manifolds in man dimension. try to unify all the quantity from physics into a geometry. That's why choosing node 很 famous， 对吧？因为那个查理这个爻，对吧？ It's a family of it's a family of manifolds that actually can capture, right? And model a lot of, explain a lot of physical equations behind the standard models, string theory, right? Can explain a lot of the constraint given by physical equations. 这个很简单，所以大家去想一想，有些东西啊，但是真正越深的数学，实际上是物理，实际上是非常简单。Actually, it's about very basic things. Okay, it's about space and time. It's about energy and mass, right? And it turns out that they're not that mystery. Okay, once you really know their relationships. So this is actually, it's not that actually, abstract 或是什么的。像我说嘛，对吧？数学家就是去 compute. Mathematics is all about computing. Physicists actually is doing very, very basic observations. They're trying to describe the phenomena with very, very basic. And now, actually, what's hard is that now let's think about what's in our problem, right? What is learning? Right? What is the problem behind learning? Right? So yes, we can talk about distribution in abstract. This is the problem, right? So in statistics or probability, everybody start with px, right? I give you distribution Gaussian. I give you Laplacian. I give you some distribution, right? As if you have it. No, we never have it. 我们从来都没有 distribution， 对不对？在现实生活中，你什么时候真的会有 distribution 呢？ In reality, you always start with data. You only have samples on the distribution. You never have P of X. You only have the empirical distribution, right? You only have set of samples. Right? In the textbook, I give you example, 8 points, right? On a straight line. That's it. You only have 8 points, maybe 10, maybe 500. So what? There's just a bunch of points on the line. Why in the world you should call it a line? Who gave you rights to do that? Think about it, right? Why? Why do you choose to not call it those lines, those points are not on the plane? Think about it. It's not that easy, okay? Right? So turns out there are many ways I can explain the data. Right? And think about just what's wrong with just memorize those points. Nothing wrong. Right? I have a very good memory. I remember all the 500 points. Right? Everything I've seen, I have a photogrammetry memory. Right? I don't want to generalize anything. Or you see, right? All the points, let's say on the plane, 500 points on a plane. I just think that they're just samples from some uniform distribution. Of course, it's possible, right? Even they lie on a straight line. Well, we're lucky. Right? Well, on a million, all the points happen to lie on all the points I draw happens to that. I think it's still possible, right? Remember? There is even a chance all the points repeat itself on the same location. Lucky me. What's wrong with that? Right? Or they come from a Gaussian distribution. Every point is possible. Maybe a little bit uneven. That's it. Nothing wrong with this. Right? Any points lie on the RD, they just come from some stupid Gaussian. Right? They can perfectly explain the data. At least that's one possible set of examples from this distribution. Then I can also calculate a little bit, right? If the data form an ellipsoid, right? It's not a uniform Gaussian. Maybe all the data concentrate on this ellipsoid, and I calculated those empirical or correlation, right? This is actually what the attention is doing, okay? How the data are correlated with one another, right? And computed this is the ellipsoid. I used all this data very much. This ellipsoid already contains all the data. This is probably a better fit. Although there's a lot of internal structures, I don't care. What's wrong with this? Nothing wrong. Or I can maybe approximate the data actually rather than this ellipsoid, maybe on this kind of curve, right? I can fit it very closely, maybe on some surface. Size on this is a stupid ellipsoid, right? There's actually a little bit of surface inside. I can choose that very close to likely, if I'm lucky, right? If there's a God, it's actually indeed this comes from that surface. Then the central beam will be lower, right? Because it's a smaller surface. or I just remember those points about service. Who to decide which one is better? Right? This is actually a very fundamental problem for statistics. Right? So this is actually just people don't think about it. When you learn all knowledge, right? You take it for granted. You never think about it from the first principle, right? What's actually given us points? You guys take for granted, oh, we start with Gaussian, we start with some exponential family, start with some family. No, who gave you that? Who are you to make these assumptions? You should ask why it's correct. So but how do we approach this? Well, obviously, right, we know if data indeed has this one, it has higher entropy. Right? To code data flow from this distribution, you pay a price. This is higher, the volume is larger, the uniform Gaussian, right? And the ellipsoid is smaller, has a smaller volume. And the surface you can find is smaller, right? Volume is a lot smaller. Right? In some way, in X internal entropy, if the figure data, at least this somehow give you indication, right? I prefer the one with a smaller volume to cover my data. Okay? You may have a trouble. What is trouble? This guy has no volume, right? They're just points. Well, we'll talk about that. How do we unify this? Okay, it's a different story. Right? Because the surface at least has higher dimension than just individual points, right? Points only has 0 dimension, right? So those are the things you should ask yourself. You have never asked yourself those questions. That will make you a very good researcher, okay? Right. So you think about it. What is your criteria to choose which one to explain your data? Now, here's a standard way. Remember, if I have data actually has distribution P, this is the ground truth. I actually draw X from the probability P. However, I don't know P. Okay, I think that X is drawn from some distribution Q. So for example, Xi. Although in true probability Xi shows up, is Pxi. Okay? It's Pxi. However, I don't know that. I don't know that. I only think this from some Gaussian. Maybe the Xi according to some distribution. I think it's from Q. Okay, Q may not be different, maybe different from P. I think then what's the price I pay? Right? Maybe according to P, Xi is 0.5. I only have to pay 1 bit. But maybe Q is set is 1/8. You pay 3 bits. Remember? So it doesn't really matter. I just using Q to encode. Think Xi has the probability Q. I use Q to encode X. So then this is the price I'm going to pay. If I have n samples, Xi, they're drawn from P. However, I just trade them from Q because I know what Q is. I guess Q. Then this is the price side. This is the bag I need to the volume I need to store X. Okay? Understand? Right. Then this is all possible to this one, right? Because the actual X is actually shows up with P, right? So this kind of shows up the frequency. X shows up with frequency. Right? Let's do make a cosine. You pay the price instead of okay? You spend that many bits to record the cosine. Also, say actually using actual probability. Turns out there's something very interesting, right? If for some magical reason, I guessed the P correctly, so this is the price I call. This is the true entropy of the data, right? P log P. 对不对？ It actually shows up with frequency P and with the price I pay is log P. You remember? This is actual price. If I know the ground truth, know the correct, I guess the distribution right. Now, what if I guess wrong? I use the wrong code book, wrong frequency to code the data, wrong distribution to code the data. Then this is the price I pay, right? This is how many bits I need to store X on average. Now, very interestingly, turns out that this is always larger than this one. So if you guess the distribution wrong, you can calculate in the entropy, the coding length, using the whatever distribution you decide to code the data. And that one is always strictly larger than this one, unless Q and P are equal. The equality holds only if and only if under very general condition, Q equal to P. Otherwise, it's always strictly larger than 0. 明白吗？ So this is a very important concept. However, this still doesn't tell me what P is. However, give me a recipe to search for P. I can try different Q to compare which one gave me a smaller number of average coding lengths. 明白吗？我就把它装下去，小的我就 prefer， 对不对？ So hence the idea of compression. For me to find the actual distribution, I know this is the minimum. I cannot get lower than this. Okay? Any wrong guesses unless this is the lower bound. Although I don't know where the lower bound is, but at least I can try. I can do gradient descent. Right? I can try if Q belongs to a family, especially paramount theta, to gradient descent on this guy. I can always try different Q, so that to reduce the average, the coding length, I encode the actual data from the samples. Hence the idea. Hence that's why it's always compression. Compression will allow you to find the actual distribution of the data. Okay? Although you probably never know you actually reached it, but at least it give you a direction to go. So that's actually the basic idea. Very simple. So you use the coding length as the measure of the volume. 好吧，你有一个测量体积的方式，一旦你知道你测量，那就是哪个小哪个好。一个买西瓜，哪个大哪个好，对不对 ？If you can measure more mass， 对不对 ？Bigger one is better, right? The heavier one is better. No problem. But you can measure. So it's just a measure. Hence, this gives us a recipe to approach the distribution. Compress. Right? Now there's a possible way. Okay, then now you can think about it. So as you can see, once you have the training, it's actually you can go very, very far, right? Now, once I know how to measure this, then I can actually say, right? The first approach is the statistician tells you this. Okay, statistician will tell you the analytical one say, the data I believe it comes from exponential family, which is generalization of the Gaussian distribution, right? Or from some sub-Gaussian family. They pre-specify the family, but they don't know the sigma, CC. They don't know the bias. They don't know the covariance. Okay? They don't know some parameter of the family. But it must be from this family. Also, physicists usually know where this comes from. They're usually from physical model. For example, the level of the electrons. So they may come from some Bernoulli distributions, from some Laplacian distribution. Okay? But then there's a physical model behind it. Right? You can see all data must from some parametric family. Hence, they look for which parameter give you the lowest coding rate. Alright? Actually, that is the idea behind the Hall-field neural networks. Right? Minimize the free energy. Actually, the reason Hinton and the Hall-field won the Fields Medal, Turing, Nobel Prize is that, right? They believe the neural network is actually they're using some energy from the physics motivated energy to measure the neural network. Believe the neural network should minimize the energy. Remember? I believe, it comes from some distribution. The ways should follow certain distribution, motivated by some physics. Although I don't think they are quite right, but anyway, they got a Nobel Prize anyway. But right, that's one approach. Some physical justification, some mathematical guesses. I believe the data comes from some variable, then I minimize the theta. Right? This is actually called maximum likelihood. right? You find the most likely theta, give you the highest likelihood, right? The second approach is that empirical, not parametric. How do I know the family is right? What the heck is a family for natural images? Right? 你知道那个 David Mumford, right? The fields medalist. 得菲尔兹奖的 David Mumford，朱松纯的老师，对吧 ？Spent about 20 years search what is the distribution, analytical distribution for natural images, right? Random fields, Isaac model, or random fields, Markov, he tried everything, right? Turns out he's not going anywhere, right? 我的书里面讲过这个，对不对？朱松纯还在努力啊。So what about something what about we don't know this darn thing, right? Who knows what the heck this curve is, right? 因为红的跟蓝的可能 dimension 还不一样，对不对？可能这个是高斯，那个可能是 exponential. Who knows, right? Some weird maybe 是查理奥 manifolds, right? 没法写成任何高斯，对不对？那宇宙是九维的 dimension, right? Who knows what that looks like, right? But how do we approach such structure? We know they're low dimensional. We know they're very thin. 它们很细很瘦，对不对？很薄。But that's about it. But we cannot say much about what the shapes looks like, right? How do we approach that? Another way is that 从大到小 or shrink gradually. You find a way to converge to those things. Right? Go from outside. Almost like remember we have seen the power iteration, right? How do we find the principal component, the first one? We start random guess. Let's say with about power iteration. Let's compress, get rid of noise, right? Try to go for some big one, for something without knowledge. Trying to gradually shrink down the data, or find where the data is, the distribution actually is. 有包围啊。农村包围城市啊，这个从来的，能 actually find where it converges to. So compression is a mechanism. But regardless, you see, doesn't really matter. Right? You have to reduce entropy, gradually shrink, try to fit your data, or you do the parametric family. It's always doing compression is the recipe, right? Pursuing the dimensionality. So now the question is, all roads, how do we do this? Right. Because it doesn't matter. All roads to Rome leads to Rome, 对吧？不然你 parametric approach has 这个 general 的shrinking approach, right? Also do right. How do we reach? We don't know where the heck this is, right? This guy this one is hidden in the millions of dimensions, right? Billions of samples hidden in the millions of dimensions. Where are they? Which surface it lies on, right? So we have to start from somewhere, right? How do we go from anywhere and want to reach to that place, right? Why people say all roads to Rome? 大家知道这典故怎么来的，对不对？所有道路通罗，条条大路通罗马，为什么？大家知道典故来了吗？对。因为罗马conquer the whole world, right? They actually build the roads, right? Before they send the army, they actually build great roads. They build the roads to reach the world, right? Hence, all the roads can reach Rome, right? 兵马未动，粮草先行， right? So it's actually build the road. So in order for you to reach that place, you have to build the roads to reach the whole world, right? So you can get to it. So that's the first step. How do you go from Rome to reach the whole world? You add noise to the data to reach the whole world. Okay, from the data, start from the data. You gradually let it grow, become fatter and fatter, right? Cover the whole space. Now, once you go from here, adding noise, gradually conquer the world, right? You need to go back, right? Doesn't really matter. Step by step, you go way back. And follow where your world comes from. You learn that reverse process back to your world. From anywhere in the world. Now you can go back to the surface where the data come from. Right? The idea is actually very, very simple. Unless, okay, Unless you can find a better idea, okay? This is the best idea we have yet, right? Maybe we're sitting in the blind spot, okay? Maybe there's a better way to reach that, to identify where that is, okay? I think that this is a very natural approach. I build the roads to reach the whole world, and then I remember where I come from. Okay? Go back, learn back process. So this process is exactly adding noise diffusion. This process is exactly removing the noise every step I add and another way back. This is called noise. Okay? Right. So, add noise. Start with the data. Right? I grab the adding noise. T is larger and larger. I'm T, right? Add noise. This is actually diffusion process. T is actually see this is Gaussian, right? Add a Gaussian. Every point it's grow, it's grow, it's grow. Right? Every single points become bigger, bigger. Gaussian. Second connected. Remember the book cover. Right? It's bigger and bigger. And the noise reach until T gets large, right? The variance of this is T squared, right? The variance of it grows like T squared. Right? It's very simple. So as you can see, start with the points on the data distribution from Rome, you eventually reach every corner of the world. Okay? Then you don't have to go back. Remember, we're having to go back. Right. So indeed, if you add noise, this is exercise. Everybody should go through this. Right? If I add noise to some random distribution, any distribution, no dimension or high dimension, doesn't really matter. If you add noise to it, you add Gaussian noise to it, the distribution looks like this, right? Take a convolution. This is the actual Gaussian distribution, right? Take a convolution with it. And you actually can prove, right? If you add noise to it, the entropy of PT, when T grows, entropy always grows, always positive. 所以加噪声啊，这个世界的噪声为什么会越来越大？有个封闭系统，对吧？这是热力学2.0，对，大家atom 在撞嘛，撞击在相互在加噪声嘛，对不对？热在扩散嘛，对。So every become more uniform, right? So actually the whole world of entropy is always increasing. Alright. 理论上，一个封闭系统的熵是不可逆的。Right？ 我们的宇宙的熵是不可以的，对吧？几万亿年以后，几千亿年以后，可能就大家都变成 atoms， 对吧？我们就说，看 ，But we're not there yet。但是，熵在什么情况下可逆？外部的 energy，right？ 所以我们希望我们的黑洞不是单方向的啊。Hopefully there's a God there, right? So they can change the entropy. Maybe they don't know, right? So if our world is a closed world, we're dead, right? We're doomed. But if not, if you can inject energy into the system, you can make it lower, right? 就跟冰箱，对吧？加上这个插上电就可以制冰了，对不对？水就可以变成冰了，而 entropy is much lower. That's a perfect example. 就交换热嘛，把热交换出来 ，right？ 把 noise 去掉嘛，是不是？把水分子的 noise 去掉，就变成冰了嘛，变成 crystal 了，这很简单的道理，对不对？但是你得插电啊，你插电就冰就化了，对不对 ？That's very simple. So this is actually a very simple idea. Right? Now, of course, you have to prove this. Actually, this is a good calculus. I think, well, guys, there's a 有些东西啊，我倒不说这个课程 I don't require you to be very mathematical, right? But there's certain things are very basic proof. 我们说数学学数学，对吧？把概念搞清楚。Right? There are three types of proofs, mathematical results, right? Right? At least we learn mathematics. There's three types of proof, right? One type is that you will never bother to learn the proof. It's too difficult, okay? You only learn the results, you use it. Okay? The second type of proof is that you go through once in your life, okay? You do understand it's correct, check is correct. The third type is very important. Not only you go through once in your life, you really need to understand it. Even apply the techniques for future. Okay? This is one of them, right? It's very basic to prove adding noise. This is very basic proof. Of course, I skipped some of the steps. I mean, you actually can go. It's very much basic calculus with the integration by parts. For example, from here to here is really just integration by parts for multivariables. Right. So you can actually go through that. Appendix B2. This is exactly a proof you need to go through. Okay, at your level, right? You should not only be able to go through it, you should be able to memorize it, right? And know it where it comes from. Next time, you can actually show to people. You know how it's derived. And the next proof, this is the second type of proof, right? Some of you may want to go through once in your life. It's in the appendix, the proof, but you don't have to memorize it, right? It's for special people, right? But you probably need to go through, take a weekend, have nothing better to do, right? Sit down for 3 hours to go through the proof once in your life, okay? Then you can forget about it. Just make sure every step is correct, okay? You know this result is correct. That's it, right? So this is a forward process. If I add noise, the entropy increase. Okay. How do I go back? After I add the noise, I want to go back to x. Xt is x plus t. Okay, dt. If I only want to have for noise diversion, how do I estimate where I come from? 我们说嘛 ，build the road that to Roma has built the road, 对不对 ？Reach all or every corner of the world. 那你总得你 reach next stage, you need how to go back, okay? You need to know where you have to remember where you go back. So you add a little bit noise, you want to go back to that. How do you know how to get back to the world? I just do the best you can. I just expect where the norm comes from, 对不对 ？Not the word general. So this is called how we do get back from the time t, go back to time 0. Okay. Turns out that actually we use this as the equation. This is actually turns out given by this equation. The optimal solution to expect where the norm is actually we use x bar star. This is the optimal solution. It's actually solving by this minimizing this. This is called the optimal conditional expectation. The solution to this is actually given by this conditional expectation. Given xt equal st equal x. 条件 expectation. Conditional expectation. What is it? What does it look like? It's kind of complicated, right? So this is the amazing part, right? First of all, I don't know this guy, right? As for the data, I don't know where the data is. Honestly, where distribution is. Then I add the lowest to it. I have some samples, but I don't know what the distribution behind it, right? What's the data? I only know the distribution. I only know xt. I don't know x. Even I have sample of this guy, I don't know x either, right? Especially if xt is already diffused, it's already x diffused. Right? So how do I go from xt to know where x is? Turns out this is the main result that Robert's actually reported. It's called a tweak formula. I think this is the 64 paper. He mentioned the idea actually was due to tweak 1958. But then there's a Masayaki, actually 61 published paper called the empirical behavior noise. Actually stated something very amazing fact. It says that in order to do the denoising, you don't need to know x. See, if you follow the conditional expectation, right? Everybody know p. Then how do you do this? Just find the conditional probability of px given xt, right? But what is that conditional? It is a joint probability of x and xt divided by p of xt, right? Everybody can do that, right? Now take the integral. Then you need to know the joint distribution of x and xt. You don't have that. Right. Also, knowing the joint distribution, you must know the marginal distribution of x, right? You don't have x. That's the whole point. You don't have x, right? If I have x， 我去造个弯儿，我都已经知道罗马在哪里，我还去造弯干什么？对。所以 that's the whole point. That actually turns out, do the denoising, you don't need x. 所以这件事情是不得了的事情。哎，这是你看我现在发明了，大家后来都不知道，都没有意识到这件事情不重要。啊，you only need to know the distribution of time t. You only need to know the distribution of t, know the denoising. Then can see. Only thing you can see is to compute for this distribution at time t. You have a lot of sample, I still can approximate what the PT is, right? Find the gradient and go along the gradient. Push every sample c into a direction where the likelihood of gradient is higher. That's how you do the noise. 对吧 ？low gradient, low push 每个点都朝盖一个大的地方去 push， 就每个点都爬坡，同时爬坡，所有的sample同时往山体上爬，最后大家都会受在那个山体上面，明白吗？你想想啊，一个大山啊，这是 imagine， 哎，就往海啊，所有的分别的点啊，然后每个这个点都是往爬。爬到一定程度，你看是不是所有的点都会爬到那个山体上？不一定都到珠穆朗玛峰，对吧？爬到一定程度，是大家都会收敛在这些山体上面，是不是 dimension 会更低一点？是 lower dimension. That's the idea. Okay. So everybody will follow on those thin ridges. So you actually can do denoise. First of all, this is actually optimal. So you only have to estimate what is the distribution at time t. To find what's optimal denoiser. Right. So this is actually a very important result. Although, didn't realize how important. And also you can actually prove. In fact, surprisingly, right, we didn't find the. Right. Turns out, I mean, is this really this kind of denoiser? Denoiser is supposed to minimize entropy, right? But turns out nobody actually proved this. Actually, the book actually in our appendix will actually give a proof. As I said, this is the proof it goes through once in your life. Okay, you don't have to really learn all the math. You need to know every step. You have to make sure every step is correct. Check it once in your life. Okay. And learning this course is time. I think I said once in your life means once in this course. Okay. When you take this course, you better know that this result is right, where it comes from, right? Which really means that under very general technical conditions, the x is benign, for sufficient small t, s sufficient small t, it always reduces entropy. All right. So it's actually so basically you go backwards. Indeed, the entropy of distribution will decrease. At least you know you're approaching better and better, you get a better. Although you never know you actually approach to that distribution, but you know you're every step you are getting a better distribution closer to the ground truth, right? According to this, right? You're always getting a better and better Q, approaching to P. Okay, not perfect, but at least you're getting closer to P. But when this converge, it's wide open. Okay? For one family of distribution, for one assumption, it's completely open at this point. Okay? There's a lot of open problem. We'll talk about it later. So, shoot, we're running out of time, right? Oh, no, you're 50, right? Well, 50. Yeah, okay, good. So, now, as I said, guys, so one thing, if you find something for general, it must work for the special cases. Right? Remember, we started the history starting with analytical cases, PCA and so on, right? We know how to do denoising with PCA. But is this solution? This works for general, right? This works for general distributions, right? Very general distribution. But any no-dimensional distribution should work. But the subspace is a special case, so it should work. So this is actually a paper one actually proved last year. Right? Indeed, if you assume your data come from a subspace, then that diffusion operator, right, x star, that's x star t, right? According to that is exactly the PCA denoiser. 现在想起来很 trivial, 对不对? Well, turns out is actually nobody has actually really established those. So basically, just this is almost like a sanity check. You check 一下 ，special case 应该是这回事，对不对？你做了 general denoising actually works for the special case. And then what about mixture of Gaussian, mixture of subspace? The second actually can derive. Now I can derive from mixture of subspaces. Mixture of subspaces look mixture of Gaussian with low dimensional subspaces, right? So then that's the second row. You are automations, right? The subspace basis. So it turns out when the denoiser looks like this. Right. Where's my mouse? Shoot. I don't know where the mouse is. Here. Right. The denoiser looks like this. So what does the star look like? Right. Compute a UV transpose head with the two consecutive vectors and also do some software shielding. This is exactly self-attention. Data is actually, you'll see that later in the transformer. It's actually just computing how data correlated with one another, right? With a batch of data points. You're computing the UMV. And also, it's a picture file sharing you can derive the more in general cases. And again, you see that here. Shoot, where the heck is my mouse? I don't. Here. Right. You have data, you offset it with some bias, you hit it with a matrix, and another matrix, and again, do some software shielding. Right? What this looks like. Especially if you don't know the inverse, you have to approximate two factor UMVs, right? UV transpose. This is imagine this is low rank matrix. This is UV transpose, and hit with another matrix. If those none of them you know, you have to estimate them. You have to estimate that. You have to estimate the sigma k from a batch of samples. Even fit them as local piecewise Gaussians from a batch of samples. Right? That's exactly what all the attention heads each one is doing. Now, when does denoiser work? Let's do something for example, right? It's not that easy, right? It's like, yeah, sort of justify with oral spoon. But what if we know it's really that, does really we get there? When does it get there? Does it get to the entire room or just get to just the sum of the markets? Some houses in Rome, right? Not necessarily get to the entire room, right? How do you know that? Right. So this is a special case. It just tells you it's not that trivial, okay? Not that easy. So suppose I have data only have 2 points, positive one, negative one. It's a coin, okay? Flip a coin. 50%, 50% here. All right. Now, if I diffuse it with Gaussian, I get a Gaussian around the center around -1, a Gaussian center around the +1. Get 2 Gaussians. Right? When T is large, the 2 Gaussian gets wider and wider, eventually merge, right? So now, if I compute the Twitty's formula, right? This I'll leave this to you. You guys should be able to compute this, okay? Take the derivative, okay? Partial log, should be able to do this. Right? Write this down. This is the Gaussian distribution, right? And then write down the derivatives and so on. So you guys should be able to do this. So turns out if you do this, you actually get this tangent hxt divided by t squared. Now if you plot this guy, it's a little bit weird. If t is large, you start from very large t, then this t squared dominates, right? Doesn't matter. Remember, x is very much between -1 and 1, right? So xt is kind of bounded, but t is large. T grows square， 所以下面要大了很多，对不对 ？x 大概是上面 x 只加 t 嘛，所以 x 的 scale 大概是 t， 对不对？在下面 x 是 x square， 所以这个基本上这个当 t is large, this is almost zero. It's very small. But the tangent t for a very small number is almost zero. So if you denoise from a very large t, the optimal denoiser always says that you should go back to the origin. 就把都弄到中间去了，所以你 diffuse 完以后，你就回不到罗马了 ，OK？ 你回到罗马中间了某个地方去了，对不对？然后呢，这个but for small t, if t is small, and this works. 就说你如果离开罗马不远的话，你还是能回去的， and get back this denoiser precisely to what it is. Because you concentrate on this to, if the Gaussian is small, if you diffuse, you actually very much get back to -1, 1. Okay? This gives you an idea. So you cannot do diffuse too much and hope you can get it one jump. OK？ 对吧？你不能把这个世界全都，对吧？你出去不能闭着眼睛走得太远。OK？ 那很简单嘛，你想嘛，就是加噪声不就是相当于是 randomly 这样的 randomness, right? So you cannot just close your eye, random walk, and so a very long time, hope you still remember where you go back. But what you can do is you close your eye, and go a little bit step, then you look back. You remember what you're talking about. Then you can go back. Okay? Now you close your eye again, go to another step. Fine, I still go to, I remember on the next step. So that's okay. But don't close your eye either too much random noise, and you cannot remember where you got come from. You know what? So this actually, this give you an idea. Why don't we do this? Between some large time, right, 0 to t, we will see why do you have to go t very large? We'll talk about that. Because you want to reach the whole world. Why do you want to reach the whole world? We'll talk about that later. Right? Now let's just think about that. Why do you want to reach the whole world? Right? So suppose t is very large. I still want to go back. I want to the front. So, but I have some checkpoints, like T0, T1, T2, TL. I break down to I go very small steps. Then I always look back, remember where I come from, do the noise. So break down the stages. So every step will have this. Then I do these stages. Where I have TL, I can always estimate where I come from. Right? From TL-1, I add noise. Remember, I take a random step, right? Random step that I reach to somewhere here. So I have to remember how to get back, right? Short time. So if you do some calculation, it's almost like a little bit like the optimization tradition, right? Start from TL, where you are now. You want to remember where you come from, right? And you do a little bit of tweaking formula. So this step is very, so this is actually from TL all the way go back to L. But you don't take the big step. This is I already run there a long time. I'm here. I cannot remember where the norm is, but it's very vague now. Information is very vague now. I roughly remember. I closed my eye for too long, up to TL. I roughly have a very rough idea where the road is, right? I'm not too certain, but then I only take a very tiny step toward that direction. Then I reach there. Then from that point, I try to remember where the road is. I take a tiny steps. So this is exactly doing that. So every time you roughly remember at the TL, remember the further you go, your direction to Rome gets bigger and big, right? But every time give you a little bit of information. So you only take 1 over L, very tiny steps to there. Kind of proportion to the time L. So the longer, the further, so this is actually very clever, if you think about it, right? The further away, the larger L is, you're further away from Rome. So the function guy, you're raw, right? This one carries less information about where X is. So this L is large. So you take a smaller step until you're very close to raw. When L is small, T1, you're very close to raw. You take a bigger step. 对吧？所以回家的路很长，对吧？越远你就猜个大方向吧。北京是大概这个方向，走几步吧。哎，越远就是走到对吧？山海关大概对吧？想一想，开始步子大一点。都到了午门门口了，完了就往前跑，对不对？所以 this is very natural if you think about it, right? This is actually precisely how you guide yourself, how do you use the information, to go back to the original X. This is actually an idea. Now you can actually simulate, guys. Now you already have all the recipe, right? So any distribution, you add noise, you can actually go back. You can see start from random points, blue points gets all diffused. Original sample from the 3 lines, right? Then gradually you can get back to all the points get back to the row, get back to the 3 lines, right? Now, anyone want an answer why the T has to be large? Why 为什么要走回去？ 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 you don't go far enough, you don't know where to start. Okay. Remember, we're growing that darn thing, right? Remember, we're growing this, right? This is the role. We know where it is, right? It's hidden somewhere in the very high dimension space. I grow. Even to this point, I still don't know where it is, right? Even this distribution, still this is some distribution in the high dimensional spaces. What is it? I don't know. Until to reach something you know, very useful. Until to reach to some distribution you know, actually you're very certain what this distribution looks like. Okay, almost uniform or almost a Gaussian. Then you can start with this one, sample from this distribution, go back. You remember? So otherwise, you have to guess what this distribution is. If you only from that only grow up to a certain point, how do you find where that distribution is sample it? I don't know. It's probably as hard as finding this time. So then you have to let it diffuse until you reach T large enough, until it's almost with T large enough. Let me see. Value that's T. X almost X, the original X almost gets flushed out. T 表没有记不住罗马在哪 ，OK， almost then I can start anywhere. The distribution always start with Gaussian. Everything that's uniform Gaussian. Then I can start anywhere here. Then build the bridge. Then learn my flow back. So you can start from sampling this guy, go back to roll. Remember? But you still don't know where it is. You know that whatever. If you haven't reached the steady state yet, you have to estimate that shape of that distribution, right? It's almost as hard as you have to fit in this big structure. Who knows what it is, right? Again, guys, I want to say this. This is not the only way. Okay, this is one way to approach the distribution. Okay, in the history, I know like what was the began or other things, right? To try to fit the distribution. Many ways. Okay, but I guess this is very natural. Okay. Again, remember the lesson from last talk, or remember the lesson from dictionary. Okay, they may not be the best way. Okay, who knows this only way? Probably not. Right? But this is the natural way of doing. That's why you do diffuse and you go back, right? When you how to diffuse. Now the next thing is, right? 条条大路通罗马，对不对？所以 this is not only one way to do this. Even I build the roads in this way. How fast I build the steps, right? Remember I said, right? Take a step up, go back, take a step. You know, how should I pace myself? 先快后慢，先慢后快，前面长点，后面软点，前面短点，后面长点 ，right? I build the roads, right? There are sectional roads. I mean, 前面短的，前面 how, right? Nobody says. How should you build the TL? You break them uniformly. You allow uniformly, which one is better? Nobody knows. Okay, try. Alright, 就跟我们解积分，对不对？解微分方程，对不对？一样啊。How do we chop the time? Right? How refine specifically, like under the thesis, right? How to solve differential equations depends, right? What it looks like. How do I should those cubic? You know, how do I approximate those steps, right? How do I approximate those curves? It's up to you, right? So here, the rest is, you know, how do I build those bridges? When to become an engineer, right? Which one is faster? Depends on the data distribution, by the way. So I can decide how should I diffuse, right? First, how should I diffuse, or how the TL should I choose? 刚才我们 present 的是最简单的一个 case， 对不对 ？Now it's up to you. So now you know why there's gazillions of papers about the diffusion model. Then they can choose, right? How do I diffuse the data? Right, gradually diffuse to the different sigma. Why should I do it uniform? How should I do the TL? Uniform, spatial, right? So but doesn't really matter, right? You know, you do the previous formula, and they give you a different kind of iteration. right? You get to choose what the scheduling alpha, sigma is, what the T's are, right? And to do this, to get all the demon. Also, right? I want you to learn, remember, right? You have to learn a diffuser from any time T. By the way, this is actually not that easy if you think about it. You need a diffuser from at any time till looking back to rule, right? You want to get, this is different function once T changes. So basically, if you want to approximate this with a neural network, you have to train how many steps, how many TL, how many neural networks. You need to build samples to do this. Remember, right? You have to have the input, output to fit the neural networks here. I don't know how to do it. Right? That's too expensive, right? Basically, break this 250 step, you have to train 60 steps and 60 neural networks. 60 functions to approximate, okay? To learn. That's too much. Well, people try to get a little bit clever, and once all come together, as T also as input to the network, but you can do that. All the different choices, okay? Turns out, yes, you can do it, make it faster, okay? You only have to learn one neural network with the time of input to do the explanation. So again, you can name it. You confirm this for 15 days. People cite you. It's usually very simple. Yeah, fix. Then you can attribute, right? All the diffusion models, right? From random noise, in order to start, you learn all the steps and get the CFAR, Sora, Lux, better. Resolution gets higher, right? And you choose different path, different sampling schedule. How many twists? Here comes all the names, right? Now have fun because you can build a different way to go to the alone, right? Different strategy to build how pace yourself. Uniform discretization, or non-uniform. Start with data, alpha is 1, this is the virus exploding. So say basically you add x plus the tg, right? T, the virus is x squared. So the whole variable, xt, actually the virus explodes, right? Well, it's not very numerically stable. Hence, you this. Make sure that the xt, the virus is stable. Right? At least numerically more easier to implement, right? When the dimension is high, you're not handling a very large volume. This is called virus preserving process. Flow, but this is a little bit harder to implement. So people say, why not? Because this is a bit weird. The weighting is a bit weird, right? So why don't we just do something simple? 1 minus t, 1. This is called a flow matching. You give another name, okay, you become quote unquote famous, but then you are doomed to be forgotten in history, right? Just some simple fix, different tricks. So this called flow matching. People use it and very popular because they got better implementation, right? Post on Hugging Face so you guys can download it and play with it, right? So there's a lot. See, when this come out, there's a lot of people say environments, do a lot of this one. This is the BBIM, right? It's exactly this. The first people create this, and someone find out this is probably better. There's a lot of 100 papers written about this. This is very easier to implement. There's a lot of few 100 papers written about this, right? That's about it. So it's almost just basically how do you choose a strategy to implement? Okay. Depending on the data, which one is easier to implement, which one is faster to converge, and there's still, you can come up with yours, right? Maybe 1 minus t squared, I don't know, right? So you can try. So now you know where all those thousands of papers come from, right? Just to make very minor tweaks. 然后再取点名字啊。给小的 virus 要学会取名字啊，取了名字对吧？所以给小孩子取名字很重要啊。这个对 ，it's actually. But turns out there are just different roads to Rome, right? They're just a different strategy. How to build the maps. Okay, some are more refined, some are slightly slower, but they're essentially the same, right? Not very. At least qualitatively they're the same, exactly the same thing. Okay. Quantitatively, maybe they're easier to understand, easier to implement, easier to do. So 这个同学们就是搞清楚啊。Now you can, yeah, yes, the variance preserver, you can see the axis is now exploding, right? The other previous one, you can see, right? If I add noise, you can see this guy is already everywhere, right? It still works, but just allow just anyway, it still works, but it's a little bit harder, right? Because it handle a bigger volume, that's it, right? When T is large, it's harder. The variance preserving, if you add noise, fine, still around the data, right? So you handle smaller volumes, it works pretty more stable, and so on, of course, but still, it works the same way. Right. Does this work? Yes. Turns out there's some theory energy. Again, this is a third category of proof, right? You don't have to even bother to check the proof, right? Okay, we checked it for you, right? Experts already checked it. You only have to remember the results. Okay, see? So you take a lecture, we see three types of results, right? One is you have to know the proof. Second is you have to check the proof once. Third is you don't bother with the proof, right? This is the third one. Except you really want to become expert in this topic. Right? Well, my postdoc, they checked it. So suppose there's a sample that could do this, and and then you can say that when you really do very fine differences, when the L is number of steps, right? You have the whole steps, you count how many steps. Right? If L is very large, and when L is large, the TL and TL they get very adjusted. When this one becomes very close to this one, right? When the noise addition noise is very small, the noise can converge to almost perfect. So this one becomes diminished, and this is also in the denominator. The sum is diminishing, is small order of little l on the L. And so this term goes to 0. This term also goes to 0. D is fixed, L is large, this goes to 0. So actually you can show when you have a long sequence, you can break down into smaller pieces. Theoretically, this works. This actually go to the random noise, can go back to the original data distribution. This is guaranteed. However, this is actually not the best you can do, because this guy can be very large, right? Remember, this is not the best. This one is okay. This one, what if the image, right? If I use the EBAC, 100 by 100, or 1000 by 1000, or 4K by 4K, that's a problem, right? 一定很贵，这 resolution 增大，东西也很大，对不对？但是有1000乘1000的，那我哪有相应增大，对不对？那么很累嘛，对不对 ？Turns out you don't. Turns out the process, this actually can do better. Turns out that this distance only depends on the intrinsic dimension of the data. Just images, intrinsic dimension of the data. Doesn't matter how high you embed it. Right? If natural image intrinsic dimension is only 10, that's 10. Right? If you embed the image 100 by 100, or 1000 by 1000, or minute by minute, doesn't matter. Yeah, that's what I'm accomplished to do. So you can come up, so the sample size, low dimensionality plays a very important role. That's why we can approach to those, that's why with a fixed number of iterations, we can actually approach to images. It doesn't really matter, right? Say this is 100, this is a CFOX, so 100 by 100. This are 4K by 4K, almost by 1000 by 1000 resolution. Sora is 512 by 512, more or less. This is already from 1000. So that's why you don't necessarily, just because you are dealing with a higher resolution, doesn't mean that your number of steps needs to be high. Okay? Empirically, people found that. Right. 下节课呢，我跟好 now there is a question we haven't solved, right? See, remember, we started with, remember, we want to get a room, right? But we started with samples of the room. 对不对？想象一下，我们只有 room 的几个 beauty. Right, those are the samples of the room. Right? Maybe 100, 500 beauties in room. Right? Now the problem is that when I go from the world, I reach level, I converge to the room city. I can see everywhere there. Or I end up with those 500 houses. We never resolve that, right? Remember, right? Samples are 0 dimension. The distribution is collected, right? At least 1 dimension or 2 dimension, right? There are no surface. But you only have the samples, 0 dimension samples. From a measure, it doesn't matter what measure you use, right? At least conceptually, 0 dimension is always better than 1 dimension. If I care about volume, I always should prefer 0 dimension solutions, right? So if I keep the noise, remember, if I break this if I take very many refined steps, this will happen and converge to individual samples. Okay, I started with the 500 samples. Well, in reality, it's 5 billion. Okay, for images, 5 billion. That's why I'm just using 500 houses, right? So 500 samples. I diffuse. I add noise to those 500 houses to reach the whole world. Okay. Then from the world, I remember each steps how I get to back up. So eventually, I end back only back to those 500 houses. I only memorize those 500 houses, but I don't see the rest of the world. I don't see the distribution. When, other question is, when do you get to see those samples get collected? To actually span the surface. This is the question. When do the model memorize? Or when do they generalize? How do we learn the diffusion model? If I for random model, I can generate an airplane I've never seen before. In reality, it turns out that's the case, right? The continuous phase is not in the training data. Somehow they generalize. But where? How? What does that depend? How many samples? The diffusion process. Right? When does that happen? Why, under what condition does the process start to prefer this connected solution versus isolated memorization? Do you remember? I can tell you there's still a lot of, right? We'll talk about that next time, right? So there's still a lot of open question regarding how to explain memorization versus generalization. When do I actually converge to the curve rather than just some points on it? What a condition. There's still an active field about this problem. Although the practitioners don't care, right? So I was trained with billions of samples, somehow they get the curve, right? Somehow I can generate some picture that then somehow is studied in training data. Okay? And it still looks like. Okay? But theoretically, what's missing? When do you can guarantee that? Right? How many samples? What's the density? Right? Under what condition? Diffusion to noise and process, how many steps? Right? What's the choice of those parameters? What's the choice of these individual blocks? That. There's still a lot of open questions, but the next lecture we're going to see that. We're going to see that the ingredients of noise actually plays not only just allow us to do that, actually the notion of lossy coding, noise of the, we don't, in reality, people actually don't the noise to that. You stop at some level of noise level. You don't converge to that. Okay, that's a recipe people know. That actually works very, very well. But if you net all the, especially a powerful network, converge to that, you always, especially if you pick the denoiser to be very powerful, right? You can actually show you can always memorize samples. If you choose a very powerful network for a few number of samples, if you let the denoiser go to that, you'll always memorize everything. So. And the distance to theory is always actually about this. Not really allows you to generalize. The loss actually goes high. So this is actually a phenomenon, right? But the question is when? How powerful the denoiser? So basically the denoiser cannot be that powerful. If you remember every steps you leave your house, you can only remember get back to the house. You're never going to reach other part of the city. So it's very, very strange. There's a lot of mystery, very interesting question about this. There's active fields, and some of the people like Qin, Michigan actually have a series. I'm not to talk, he has a series of, this is still a very active area. A lot of top people are working on this, right, to understand the mechanism, including myself. We're still some of my pro students. But I'm going to talk about one lecture. He gave us 3 lectures at the summer school last week at the room. I'm going to cover one of his lectures. It's about how the understanding of generalization. The interesting thing is that has a lot to do with, first of all, the low dimensionality of the distribution. Second is about the lossy compression. Right? You cannot, the network cannot be too powerful. It has to allow some noise in the denoising process. You cannot denoise accurately. Okay? It's very, very interesting. Those are two very important ingredients for somehow be able to allow this to work. Be able to converge to the curve or surface instead of isolated points. And you need enough samples, and you need the distribution to be no dimensional for this whole thing to be efficient and somehow to just do the right thing. All right, good. That's for today. Thanks.